Hello friends, so let's get started our last lecture in this semester in the probability course. Um, so today I will briefly make an overview of what we have been doing during the course, what we have covered. You will have chances to ask me questions if something is not clear. And as I said, we are kind of gonna do the sequence of courses so overall we can call this kind of data science courses, starting with probability and then continuing with statistics and econometrics. So it will be, I guess, useful to get the whole picture of the probability course in order to understand what we will use in the next semesters. So basically we started with this. So I told you in the first lecture that the probability is simply the fundamental, let's say, course for the further sequence of these courses. In the next semester we will cover with you mathematical statistics and econometrics. I will briefly mention you what is gonna be there at the end of this lecture. And then, so the next academic year, we will also talk about the econometrics too. So hopefully we will meet each other on this fourth part. So, so here is the course content, what we have covered. We spoke about random events, then we introduced the probability axioms, we went through counting methods, then we spoke about the conditional probability and bias rule, which is the widely used thing in science and in different applications. Then we went to the concept of random variables. We spoke about discrete, continuous random variables, probability distributions, expected values, and then I introduced you the concept of moments. Then we concluded with the joint distributions and we spent 3 weeks on them. So let's briefly summarize the main concepts that you are supposed to understand. I admit that probably not every one of you remembers everything, but at least you must be able to find the appropriate information whenever you need this information and to understand what's going on there. So all the lectures are available, all the lecture slides are available, and if in the next courses you need, you just must remember at least that we have discussed it, and you need to understand where to go and where to see for the things. So in the first topic, in random events, we spoke about sets and subsets, and we needed them in order to introduce the concept of sample space, which is the collection of all outcomes, all possible outcomes from the random experiment. And so we introduced that some subsets of the sample space, they are called random events. So basically this is the first and crucial step, and that's where all the other courses depart. Statistics, econometrics, they are based on this action of the random experiment, and then we need to understand what are the consequences of this random experiment and how to measure this randomness. Here we spoke about events and their complements. So complement means simply that, well, if we have some event, so the complement tops this event to the whole sample space. Then we also spoke about the operations over the sets, meaning unions and intersections. So it was more or less simple. Then we moved to the probability. And so we introduced the probability measures, and we introduced them with the help of probability axioms. So basically, what is the probability? That's a function that maps subset of random events into some real numbers, and those real numbers must possess some properties, and those properties are called probability axioms. So probability cannot be negative, probability must be between 0 and 1, probability of disjoint events, of the union of disjoint events is the sum of probabilities, and so on. So we had them. So basically this is axiomatic thing, and you cannot prove them. You either believe that this is true or not, and if you believe that this is true, you can work with these probability concepts. If not, so go and invent your own theory in probability. So we spoke how to calculate probability of random events, and we introduced the multiplication principle, meaning that if you have two random experiments, one random experiment leads to, let's say, n outcomes, another leads to m outcomes, then overall you have m times n possible outcomes. And that led us to the counting. So basically counting is not that useful for our future courses, because we are not gonna use counting that much, so probably several times. So we spoke about permutations with replacement, without replacement. So it is the situation when you don't you care about the particular order of elements. So ABC and BAC is different. Combinations when you don't care about the particular order of elements. So ABC and BAC are the same. Yeah, and we also spoke about grouping. So as I said, we are not gonna use this too much in the future, but still be aware of this counting method. So probably if you're interested in playing some games of chance, then counting might be useful in order to calculate how many possibilities of the outcomes in some game. So conditional probability, this thing is very important, and we are gonna use these conditional probabilities in all the other courses, and you may meet this conditional probability in other fields of economics and in other fields of even all the other sciences, because as I showed you the example about, let's say, testing against COVID, so this conditional probability and bias rule is widely used everywhere. And it is quite important to understand this concept. So the conditional probability is the probability that event A happens when we know that event B has happened or has occurred, or simply we read this as the probability of event A given B. And we calculate this as the mutual probability, so the probability that A and B happen together, or joint probability of A and B, divided by the probability that B happens alone. So basically we normalize the probability of both events by the probability of event B occurrence. From here we introduce the multiplication law. So it's simply the rearrangement of the definition of conditional probability. If you multiply probability of A given B by probability of B, you will get the probability that both events happen. That's something natural. What is the probability that A and B will happen together? That's a probability that one of the events happen, for example, B, and then probability that A happens given that B has occurred. Or if A happens first, then it's probability that A happens multiplied by the conditional probability that B occurs after A has occurred. Something like this. So those two are the same. But then we extend the multiplication law. We extend this with the law of total probability, and here we introduce the following thing. So what is the probability that event A, unconditional probability that event A occurs? This is simply the sum of these conditional probabilities. So probability that part of B occurs, multiplied by the probability that A occurs given that this part of B occurs. And then we simply sum over all these parts. So not sure if you remember or not about the examples, but for instance, if probability, if event B is a person is infected with COVID or a person is not infected with COVID, for example. So we have B1 and B2, infected, not infected. And then A is the positive result of the PCR test. So positive result may happen when the person is infected, and that's one conditional probability. So probability that you will get the positive result given that a person is infected. And also there is false positive possibility, right? So the test may be positive when the person is not infected, right? So that's another conditional probability. And then if you want to calculate what is the total probability that the test will show you the positive result, no matter whether you have infected person or not, you simply calculate the sum of these two probabilities. So probability that the test is positive given that the person is infected, multiply by the probability that the person is infected, plus probability that the test is positive given that the person is not infected, multiplied by the probability that the person is not infected. That's the law of total probability. So you can extend this to like 3, 4, 5 possible outcomes of the event B, but the logic is the same. So event A happens under different states of event B. And then with the help of these three, we build the so-called bias rule. So what is the conditional probability that one particular outcome under the class of events B will occur given that A has occurred? So for example, what is the probability that observing the positive result of the COVID test, of PCR test, the person is truly infected? So that's the reverse operation, and we basically use the same definition of a conditional probability, where in the numerator we use the multiplication law, and in the denominator we use the law of total probability in order to calculate the probability of event A. If you understand these three things, you simply can build the bias rule. And as I said, bias rule is used in many different fields because, well, we will speak in the statistics course about Bayesian methods in statistics and how do we use them. But basically, that's the way how constantly testing, let's say, some theories or constantly testing some claims, you can update your beliefs about the probability of some events. So if you see the positive outcome of some test or some experiment or whatever, then you update your belief about the probability that this is true. You never know whether it's true or not, but if the sequence of testings leads you to the give you the positive results, then you kind of believe that this is true. So for instance, if we are talking about this PCR test, if you test the same person second time, third time, fourth time, and all the tests are gonna show in the positive result, then your belief that the person is truly infected is gonna be much higher than your belief after the first test, because first test may give you the probability that the person is truly infected at the very low level, but it also depends on the test power. So, and we also introduced the concept of independency. We use this when we discuss the independency of random variables, but it comes from the events, and two events are independent when probability that they both occur is the product of their probabilities. That's how we check if the events are independent or not. And from here it implies, so basically when you plug this into the conditional probability definition, that implies that unconditional probability of A equals to the conditional probability of A given B, and the opposite, right? So the conditional probability of B given A equals to the probability of B. So that's also the crucial thing, because in the statistics we will be testing if two events are independent or not in the real life. So for example, do we believe that the salary and the size of salary is independent of the gender of a person? That's something that we are going to test. So if we believe that it's independent, okay. If it's not independent, then probably we have some gender inequality in the labor market. Or I don't know, the results in the statistics course depends on the gender, or depends on the hair color, something like this. So maybe the blonde people have better results in statistics than the brunette people. I'm just trying to, like make up some situations in the real life when you want to test this independency. And I'm kind of giving you the examples where we are going to use this independency. So that's what waits us in the next semester. So then we kind of finished with the definitions of probability, events, and all these things, and we move to the random variables, sorry. So the random variable, we defined this as also a function which maps random events into the numbers. And so depending on the way how we define this random variable, so this function might be different. So suppose that we are, I don't know, tossing a coin and we are calculating the number of heads. That's one way how we define the random variable associated with this experiment. Or we are tossing the coin and we are calculating the number of tails. We are, I don't know, dialing the random telephone number, and we are asking the person what is the salary of this person. That's another example of a random variable. We are dialing a random telephone number, and we are asking the person age. The same random variable that is the outcome of our experiment. So we defined discrete and continuous random variables depending on their nature. Either they can take only finite set of values or infinite set of values. So we introduced the concept of the probability distribution, and that's, generally speaking, that's a rule that assigns probability to every value that a random variable can take on. So we defined probability distributions with the help of functions, with the help of graphs, with the help of tables, and all these ways must be at least familiar to you, and I expect from you that you would understand all those things later on. Because so the concept of random variable, the concept of probability distribution are very crucial for our future work in statistics and econometrics. So we defined the probability distribution either with the help of probability mass function for the discrete random variables, or probability density function for the continuous random variables. We defined also the cumulative distribution function, very crucial thing for all the next sequence of courses. You need to understand clearly that this cumulative distribution function is the probability that your random variable is less than or equal than some number. Yeah, so that's about random variables. Then we spoke and we built up the toolbox of different probability distributions. So for discrete variables, we spoke about Bernoulli, binomial, geometric, hypergeometric, Poisson distributions. So that's not the final list of distributions. There are also negative binomial distributions. In the discrete case, there is also a discrete version of the uniform distribution. So don't think that we have covered everything. So we have covered just some of the discrete probability distributions. So, and from the continuous random variables, we spoke about uniform, we spoke about exponential, normal, and standard normal. Again, there are much more of the continuous variables and more distributions we will discuss in the next semester. So some of them have the real life applications and they are derived from the distributions that we have covered here. Most of them are associated with the normal distribution. Then we spoke about expected values and moments. So I decided to somehow merge these two topics onto one slide because, as we remember from the last week, moments are expected values of the special form. So we defined the mean or expected value of x. So we denote this is mu or ex. For discrete case, that's simply the sum of these products, xi times the probability mass function. For the continuous case, that's here. So we also know that there is a second moment of the random variable, which is expectation of x squared. Again, discrete continuous case. Variance is defined as the second central moment, which is either here or here. You can calculate this with the help of the ordinary moments. So we defined also skewness, kurtosis, so the measures of symmetry and the measure of tailoredness of the probability distribution. So these, at least mean and variance, but sometimes skewness and kurtosis, are gonna also used throughout all subsequent courses, probability and statistics and econometrics. So finally we spoke about joint distributions. So what is a joint distribution? That's the concept of probability distribution applied to the random vector, which consists of two or more random variables. And that's what we are going to use almost every class, every topic in statistics and econometrics. So we defined joint probability mass function and probability density function. We defined marginals, and what are these marginals? They are like PMF and PDF for a single random variable. So you derive PMF and PDF for a single random variable from these joint things. So we also derive the conditional PMF and PDF if you know the value of one variable, what is the distribution of the other variable, given that you know something about this variable. That will be useful for us in econometrics course because we will be talking about conditional things there. So we introduced concept of covariance and correlation, measures of linear dependency between two variables, and finally we spoke about conditional expectations. So if you know the value of one variable, what is the expectation or variance of the other variable? Again, so it is built on the concept of conditional PMF and PDF. So yes, what is coming next? Okay, before we speak about this, so that's an overview of all the concepts that we have covered. So the very brief overview, though, but it gives you some sense of the toolbox that is supposed to be used in the next courses, and also you are supposed to understand at least how to operate with all the things. So if you have some questions about some particular concepts from the previous course, so please feel free to ask me. Maybe something was confusing, maybe something was not clear. So now there is a last chance to clarify your difficulties.
Not just confusing, but we don't have a review on first two exercises in home assignment number 8.
So that's about home assignments. Let's discuss it a bit later. So I need to check. Maybe so basically technically it's not possible to provide the solution for every exercise. Sometimes well, yes, sometimes the system does not allow this to do so. So whenever it's possible, I provide the solutions. If it's not possible, then well, maybe it's just not possible. It's better to then if you want to get some solutions, so better to write me the personal message, and I will respond you with some suggestions how to deal with them.
Okay.
I need to check, but yes, I remember that sometimes the system uh, usually when you need to calculate something in Excel, like some probabilities of normal distribution or whatever, so that was not possible to provide there. Whenever you just calculate everything without Excel, it's possible to provide the solution. So maybe that's what you are asking about. Okay, anything about the material and about the concepts of probability? So once again, so let me make an accent of what is the most important things, and if you don't understand these, it would be very problematic to keep going with the next courses. So basically, the most important things are the following. So conditional probability is the most important thing for the future. So particular probability distributions are probably not that important, but still they are necessary. This thing is the most important thing for the next courses. So you need to clearly understand what cumulative distribution means and how to what it represents. So basically, I forgot to put here the concept of quantile, such x that gives us a given probability. But it is also a very crucial thing to remember about quantile. Um, and also these expected values moments and what do they mean. That's the thing that is gonna used by default right from the first lecture, probably in statistics, and joint distributions. So everything that is based on the joint distribution is of the utmost importance for statistics and for econometrics. So all the other things, okay, if you don't remember how to use counting methods, permutations, combinations, that's totally fine. I mean, for statistics, probably that's not that crucial. But if you don't understand the concept of probability distribution, expected values, joint distributions, random variables, so guys, you are gonna be in trouble when we start statistics. So that's why, please, if you really don't understand the things, watch our lectures and probability, because we are going to accumulate this knowledge and we are gonna go up there. And of course we cannot build the new knowledge and new skills if you fail to understand something from the basics. So that's why I'm spending this time, and that's why I'm constantly reminding you that, please guys, uh, pay your attention to these things. Okay, so now about statistics, just to give you some, let's say, teaser, what is coming next and what to expect in the next semester. So first of all, what we are going to do in statistics. So with the help of probability now, we have a toolbox of useful things. So we kind of spoke about all these concepts, probability distributions, expectations, variances, blah, blah, blah. We went through the questions, how to work with them and so on. And we pretend that we know the parameters of those distributions. So if you remember 2 weeks ago, we spoke about some financial applications of probability. And then we spoke, so okay, there is the expected return of a stock. It equals to this. There is the probability distribution of stock returns. It has the following parameters and so on. Now, in reality, we don't know them, of course. We don't know what is the distribution of some particular phenomena. And that's what statistics does. Statistics tries to estimate or try to infer or try to guess with the help of data, try to guess these unknown parameters. And so we collect the data, sample, and we try to infer on these parameters. So how much is mu in the normal distribution? How much is p in the binomial distribution? How much is lambda in Poisson distribution, or something like this? If we believe that these distributions, they explain the phenomena around us. So usually when we work with any kind of science, we still want to build some models. Even if we are doing some engineering, we first start with models. The model of, I don't know, the model of a car, then we test this model, and then we build a real car. That's the same story for statistics. So you want to build some theoretical model of a reality, to test this model, to start asking how this model works. And then if you want to build this model, you want to know the parameters of this model. For example, in the probability, all those parameters of the probability distribution. So here is the simplest example. The simplest example just to understand how this works and how statistics works. Of course, we are not gonna do this, but that's an example that probably gives you some idea what is coming next. So if we know that the probability of observing heads for a fair coin is 0.5, so the well-balanced coin with no chance, with equal chance of having either heads or tails. And then you have a real coin. You have a real coin and you want to test whether this coin is well-balanced or not, or whether this coin is loaded or failed, right? So how can you check that a given coin is fair? So you need to make an experiment. You need to toss this coin several times and count how many heads you observe. But then the question is, okay, if you toss the coin 50 times, for example, and 26 times you observe heads, 26 is not exactly 0.5 of 50. Is this possible for a well-balanced coin to have 26 out of 50 times? So, does this contradict your belief that the coin is fair? Probably not, right? So probably 26 out of 50 is okay to claim that the coin is fair and everything is okay. What about 27? If you have 27 heads out of 50, is this still consistent with your belief that so the coin is balanced and the true probability is 0.5? What about 30 times? Is this possible? What about 40 out of 50 tosses? Is this still possible under the belief of a fair coin and under the belief that this coin is okay, but we are just lucky? So we can get lucky, right? So and get out of 50 tosses 40 heads, even if the coin is well balanced. There is some small chance to get it, to get this outcome. So that's a statistics. We collect some observations from, let's say, some random experiments, from the observations, and then we want to infer about the true parameters of these events that we observe. How likely is this to get the following sample, to get the following data, if we believe that something is true? If this is highly likely, then okay, probably we cannot reject our belief. If this is extremely unlikely to get these observations with these beliefs, then probably our beliefs are not true. So that's what statistics is gonna do. And we will work with the data, we will work with the data samples in order to infer some parameters of the probability distributions, and in order to answer questions whether something depends on something, whether something is connected to something, and so on. So it also must be rigorously built because, well, there is there is a phrase of Mark Twain, I guess. So he said something that there is what he said. So he said something like there is a lie, there is an extreme lie, and there is statistics. So if you don't want to have to prove this claim, and if you don't want to have statistics as a way to to prove what is necessary to some, let's say, uh, to some individuals, then we need to understand how statistics must properly work. That's what we will do. Um, so how econometrics is different to the statistics? So remember Cobb-Douglas function. We use this for, let's say, to describe the production function of a firm, and we have, let's say, several values here. The y, which is the quantity produced, x1, x2, which are inputs, and ab are parameters of this function. Okay, so the question is, if I observe some data from the firm, if I know how much the firm produces, if I know how much the firm uses of x1 and x2, how can I calculate A and B? So that's the question of econometrics. First of all, we want to estimate some economic models. You have a theoretical model, Cobb-Douglas function. Now, you have a given firm or the collection of firms. How can you infer what are the parameters of this Cobb-Douglas function? What are these A and B in practice? That's econometrics answers you. Or for example, well, more advanced things that are not gonna be calculated in the first part of econometrics, but in the second part of econometrics, we will try to estimate the demand for a good. So some demand curve, price equals blah 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 quantity. That's what econometrics does. Another application of econometrics. So suppose that the government imposes restrictions on selling alcohol on the public holidays. Why? What is the purpose? So probably a government believes that it will reduce the crime rate, or it will reduce the number of car accidents, or something like this. So we will test whether it's true or not, whether the government restriction helps to prevent some crimes, or helps to prevent some car accidents, or something like that. Because, well, we in this case we can prove, so these measures are efficient or these measures are not efficient. And also we need to collect some data on this. Or, as I gave you an example, is there some gender, race, or age discrimination in the labor market when the person applies for a job, whether there is some special treatment against, let's say, women, or against young people, or against the old people, or something like this, if there is something or not. That's the way how we can answer these things in econometrics. Or let's say, do the data scientists have higher salaries than other professionals? Also, we can claim something like this. Well, what's the special thing in econometrics here, that if you cannot randomize, then econometrics proposes the other way of making causal inferences. So what does this mean? Causal inferences means that we have some treatment, we have some action, and this action leads to some result. So it has some cause, right? Well, usually we can do this with the help of experiments in other sciences, but obviously we cannot make experiments over people. We cannot make experiments and ask people to go to the data science and to some other fields and then kind of measure their salary in the future. So it's not ethics, it's not ethical, it's not, let's say, even possible in practice. And the most exciting thing about two courses about statistics and econometrics that we are gonna study a little bit of Python programming. I hope that you are so excited about this. Why? Because, well, if you want to work with data, if you want to work with the huge data sets, there is no other way to do this. So we are not gonna calculate things on the piece of paper. We are gonna make some calculations with the help of this programming language. So if you're somehow interested, so probably you can spend this New Year holidays watching some courses on YouTube, Coursera, or some other resources on the Python for statistics and for data analysis. It will help you. Of course, it is not necessary. I mean, so we will start with the very, very basic things. And you are not supposed to be, let's say, an excellent programmer in Python, but we will start to build up our skills in this, and I hope that it will also pay off in the future. So that's our plans for the next semester. I hope you are excited with this. Um, yeah. Any questions about this?
Not yet, but I guess we will have later on.
Yeah, we have a lot of time. In the next semester, we have something like 18 lectures on statistics and 9 lectures on econometrics, plus exercise sessions. Yeah, we will have a lot of fun there.
So will we go deep in data science?
That's what we are gonna do. Statistics and econometrics. Those are two first steps into the data science. Of course, first of all, we need to understand clearly what data science means, because it's nowadays people call data science whatever they want to call. So we are there with the probability, because the probability is the first step into data science. So statistics is the second step to the data science. Econometrics is the third step to data science. And then you are departing to something like machine learning, big data things, and so on. Well, if you will be successful enough, that's something like motivation. And if you will be able to cover, let's say, essential things in mathematical statistics fast, then I will give you some, let's say, some simple things from the data science, because guys, this is the huge field and you can spend the whole your life into doing this. So that's why, well, we are kind of restricted with the time, and of course I will give you some steps there. That's why the answer is yes, we are already doing this. We are already doing data science. But first of all, you need to, rigorously have let the first grade of data science classes, then the second grade of data science classes, and so on. So nobody reads Dostoevsky in the first grade of school, right? So you need to first know how to read the words, and then you go to some difficult things. Okay.